Good evening, everyone. Let's start the NPTEL live session for the course Advanced Transition Metal Organic Chemistry. I'm Disula Sharma. So today we will be taking up the B6 assignment questions and we will go through all the lectures, whatever has been covered in the B6, that is from lecture 26 to lecture 20. Before starting that, I will just give you a brief that up to lecture 25, we have seen different kind of ligands. And lastly, we left at a position where we talked about transition metal arene complexes and their certain reactivity. But the reactivity portion has not been covered yet. So we will continue with that particular reactivity of transition metal arene carbonyl complexes. So as you can see in the lecture 26, what we saw that how can we prepare arene metal carbonyl complexes? Initially, we were having just the transition metal arene complexes, which is binding with the metal in eta 6 or eta 4 or eta 2, or sometimes in eta 1 fashion also. So now when we have to have a mixed ligand that we were looking in the case of transition metal cyclopentadienyl carbonyl complexes, where there was one substitution, one side it was CPD, and other side it was CO, which we call as heterolytic ligands, where the ligands are different, and therefore it goes from a sandwich to a half sandwich thing, because now the other side is when it is going to this first it is heterolytic, different ligands. And this metal carbonyl arene complexes, they come under the category of half sandwich complex. So here we have to talk about its preparation. So it is simple reaction where we can take a metal carbonyl halide in presence of arene, which we want to coordinate with the metal, and AlCl3, which is a Lewis acid. So this Lewis acid, AlCl3, will take up this chloride, and therefore the position would be empty with a loss of two carbonyl, because one carbonyl is going to give you two electrons, and it is going to substitute your arene ring. That one Cl has been taken up by the AlCl3, making it as AlCl4 negative and giving a positive charge on the total complex, full complex of manganese, where two carbonyl has been lost. So to balance the charge, the benzene ring is, arene ring is here, which is coordinating with the manganese, and followed by three CO ligands, which is coordinating with your manganese, giving up a positive charge. So if you will calculate your its total valence electrons of this particular species, this arene will give you, I'll draw some cell. So, so here is your arene, carbonyl, and total charge is positive. So this arene, which is nothing but a benzene ring, it will give you the 6 electrons. Manganese is 25, which is D7, 7 electrons. One carbonyl will give you 2. When you multiply it by 3, it becomes a 6 electron. And therefore, 6 plus 6, that is 12 plus 7, it's 19 valence electron species. But we can't forget that 19 valence electron outside it is positive. So 1 minus, it will become an 18 valence electron stable complex. So this is how what we started with here. And molybdenum here was 7 plus 10 plus 1. It was an 18 electron valence electron complex. We ended up having an 18 valence electron. The only thing, the difference is here it was a neutral complex, where it is a charged complex, where both the cases, sorry for the mistake, where it would be manganese. This is not molybdenum. So the only mistake over the only thing is over here that oxidation state is still of the metal is +1, because of the Cl it was +1. Here due to the positive charge outside it is +1. But the case when we have treated it with the Lewis acid, it has converted it to a neutral to a charged species. This is the one method from where we can prepare your arene metal carbonyl complex. Looking at the second thing, where other preparations are there. So one method is just to treat it with the arene and with the Lewis acid. The second is arene substitution. If you already have arene over there, or if you have other ligands, where you can substitute it with a arene, because arene will give you, if it is binding as an eta 6, it will give you 6 electrons. So any moiety which can have this total combination of 6, it can go out. For example, one arene can be replaced by the other arene, but it happens only at high temperatures. So therefore, this arene has substituted, or we can say not substituted, we can say it has exchanged. So this exchange has happened, and this arene has come out like this way. Now, if we have an acetonitrile, which is normally a solvent, and that has a coordinating capacity with the metal, and CH3Cl itself will give a 2 electron. It's a 2 electron moiety. Similarly, pyridine is a 2 electron moiety. So when arene is here, which is a 6 electron, and CH3Cl, which is 2, where 2 into 3 becomes 6 electron. So one arene will exchange all the 3 CH3Cl, and therefore the solvent molecule will come out with arene getting attached with the chromium, maintaining whatever the total valence electron was there, it was maintained. The charge was maintained. There was no additional charge over there. So this is another method where you can have from a neutral complex to a neutral complex where ligand exchange is happening and no charges getting accumulated on the complex. The another thing is pyridine, where pyridine is also having 2 electrons, where this will participate as a 2 electron and arene can face all the 3. And since we have BF3, so when pyridine is coming out of that reaction, so it can coordinate with BF3 very easily, making an adduct kind of compound. I will show you. So what we are actually talking about. So this is pyridine 3, molybdenum carbonyl 3. We have taken this example BF3.OE. So this is also where lone pair is actually coordinating with your boron because this is a Lewis acid. So this is Lewis acid and Lewis base adduct. Completely this becomes a Lewis acid, Lewis base adduct. So here it will calculate, it is 3 into 2, 2 electrons, this 6 electrons plus 6 electrons. This will become an 18 valence electron species. Now, because in presence of this particular adduct, it can, and in the presence of this arene, which is a 6 electron, it will give you arene, which has replaced your pyridine. This again is 6 electrons, 6 and 6, which is 18 valence electron, plus pyridine is coming out. Now, this pyridine has a tendency so this pyridine having this lone pair, it can directly bind with your BF3. Therefore, it is giving a side product of this pyridine BF3, where diethyl ether can come as a solvent in the reaction. This is how. So this is called ligand exchange method. So I have just taken one example. You can try out other examples also, where you will find that total number of valence electrons is remaining the same. Second thing that it is just a ligand exchange where the same number of electrons has to come into the picture because to maintain that total charge on the complex where we are going from neutral to neutral, which is not possible in case when we are taking an arene and AlCl3 that is a Lewis acid. Now, the second thing is like we have to look at the structural aspects of this kind of half sandwich complex. So firstly, this is half sandwich complex again. These terminologies are important. And we need to see what kind of bonding parameters are there. For example, if you will consider, so these numbers are nothing but your bond distances. So these are in picometers. So carbon and carbon of this arene, carbon and carbon which is having a partial double bond character, it is having 140 picometer bonding. Whereas this carbon with the chromium, which it is the chromium is connected to all the carbon which is in resonance. So that's why we have taken just an average that is 172 picometer. And chromium with the carbon of the carbon, because there are three different kinds of carbon. Carbon of the arene, carbon of arene and chromium, chromium with the carbon of the carbon. So this is 184 picometer. Longer the distance, shorter would be the strength, like lesser would be the bond strength. So this is just a structural aspect of it. And carbonate C and O, the CO bond distance is 114 picometer, which is the strongest bond among all of them. So this is eta 6 benzene tricarbonyl chromium, the name of this particular complex, which is having a piano stool geometry. We have already read these kind of geometries where somewhere it is tilted also, somewhere it is like piano stool or complete sandwich or half sandwich. So this is a geometry. And arene is having a six-fold symmetry. There is three six symmetries existing over here because it can have like all the things of symmetry, and we can just one proton if you are moving. So we can't just tell about like one is He and one is He. All are same. So they are having a C6 fold symmetry. So this was some description about the structural aspects of arene metal carbon complexes. Now we are just looking at different aspects of its different moieties attached on the particular complex and how they are going to react with different reagents or substrates that we are giving. So the title says that we are talking about its reactivity. Earlier we were looking at the structural aspects. So for example, this is the structure, they have elaborated it. So if we have a certain moiety on that arene, earlier we were just looking at this unsubstituted arene, which is coordinating with your chromium and having carbon, carbon, and carbon. Now this moiety is there, and if it is having a heteroatom, having a heteroatom matrix substitution, it will increase the solvency. That means easily the solvent will come, it can dissolve in a particular solvent. And these hydrogens over there, they are being acidic in nature because of this arene being attached with the metal. So because of that, it is having an enhanced acidity. That means it can easily be lost as H positive. Similarly, the H which is directly attached to the arene, it is even having more enhanced acidity. That means it can easily be gone as H positive. These are the reactivity aspects of the proton and the carbon or the other thing. Now we will talk about this carbon of this arene. They are having an enhanced nucleophilic substitution. So if we compare a normal benzene ring and a benzene ring which is connected with a metal center, this complex which is having the carbon over there. So these arenes are more prone towards the nucleophilic substitution compared to when we have a benzene because of the negative charge. Here the negative charge is getting distributed with the metal. So when negative is less, the charge is less, then the nucleophile can easily come and attack on them. And as a result of this enhanced nucleophilic substitution, we cannot have an electrophilic substitution over here. So for a comparison purpose, we will talk about all the points in one or two slides later. So the last point is of the steric hindrance. If is of this metal moiety, which is coordinating with P carbonyl, it will not let any nucleophile to tap from this particular position. It has to come from the other side. So there are endo-exo positions. So we have to see wherever the metal carbonyl positions are there, the other side attack will happen because of the steric hindrance will happen. So what we were just talking about, as I was telling, that if we have normal benzene and if we have arene metal carbon complex, so here if one aspect we will take electrophilic substitution, that would be more over here and less over here. Cross does not mean that does not happen. I'm just talking about on the basis of like comparison. And if we talk about the nucleophilic substitution, in benzene, it is less compared to the arene which is connected to the metal. The reason being very simple, because when you have an arene, and if it is free arene, it would be having more charge density around it. So if we have simple benzene ring, it is a neutral moiety, aromatic, pi electron density. So it is already negatively charged. Therefore, attacking on an electrophile becomes very easy. So electrophilic substitution becomes very feasible. Whereas if this ring now is connected with a metal having electron withdrawing groups, carbonyl. These are electron withdrawing groups. So when we have these electron withdrawing groups that too connected with a metal, they will try to take up the electron density from the metal because they are directly coordinating with the metal. So the electron density, the dipole limit is towards these carbonyl, and then metal will take up the electron density from this particular aromatic species. So that negative charge or that electron density on that arene moiety is not reduced. Negative charge or the electron density has now been reduced. And because of the reduction in the electron density around that element, now it is more prone towards the neutrophilic attack rather than to attack on the electrophile because now it is getting more positive and now neutrophile with a negative charge can come and attack on it. So this is how we can have a comparison between the arenes. That is why it is said that electrophilic substitution reactivity is lower than the free benzene owing to the inductive effect of the COCO3. Inductive effect is nothing but that charge separation thing. Because of this cobalt moiety, which is having the carbonyl, it is increasing that it is decreasing that electron density around that area. Therefore, the electrophilic substitution reactivity is low, whereas nucleophilic substitution occurs readily. So the concept is very simple. If somewhere one moiety is prone towards electrophilic substitution, it can't go for the nucleophilic substitution at the same time because if it is having less electron density, it will prefer to have an electrophilic attack. If it is having more electron density, it will attack on the electrophile. So this is where we compare the normal benzene with an arene metal carbonate. Where carbonate also plays a very important role. If somehow we have a electron donating group attaching with the metal, so it could be having more effect or if we have a certain comparison in continuation with this. Okay, so if I am having this array, where if I use suppose a pyridine molecule, which we are taking as electron donating group, or some other example if I take. Suppose if we have any group, just in case of the inductive donating groups. And if we have a simple benzene ring, and now we have a benzene ring which is having a metal and connecting with an electron withdrawing groups. So which one is more likely to agree for the nucleophilic attack compared to this one and this one? Because now it has increased this electron density on this increased electron density because of the metal moiety, and this is the p arene, so it is not going to change anything. It is reducing the electron density, and that's why this will be more towards the nucleophilic substitution reaction. And the trend goes opposite when we talk about the electrophilic substitution reaction. I hope this is clear. Now, on the basis of this concept of electron density around the arene, coordinating with the metal, carbonyl, and all those things, now we will see how the reaction actually takes place. So we have a complex which is having a moiety of fluorine attached to the arene. Now, fluorine is an electron withdrawing group. So already it is having, we have already talked about that this makes the proton very acidic. And also because of this less electron density on the arene moiety, it becomes even more prone towards the nucleophilic attack. So as you can see, this structure is nothing but like this. If you will just, so this is a nucleophile having a lone pair, and it can easily attack on the position, that it's a position where the fluorine is attached. Now this, earlier it was coordinating, the metal was coordinating with all the carbons having an eta 6. Now it is coordinating with 1, 2, 3, 4, and 5. It becomes an eta 5. And since this lone pair is attacking on this its position, so here, because its lone pair is now, it has involved in a bonding, therefore the positive charge has come, and the total negative charge is on this particular species to maintain that charge on the compound. And now since we have a fluorine, and this hydrogen becomes very acidic because now it is coordinating with the nitrogen. So if it goes, it will regain its lone pair and therefore it becomes NR2. So therefore, this F negative will attack on this H, releasing the acid H hydrofluoric acid, and therefore NR2 will come over here. And this is what we call a nucleophilic substitution reaction. Because if we'll see F will also come as F negative. NR2 is also coming as NR2 negative. So one nucleophile is getting substituted with another nucleophile, depending upon the condition where it is happening. And the reaction is happening when it is going from eta 6 to eta 5 transformation and then coming from eta 6. So this eta 6 to eta 5, where it is involving in a cyclic 500 ring, and then it is again going back to its eta 6. Just the change of one nucleophile has been changed to the another nucleophile. Another example of this having a nucleophilic substitution reactions. So if you see clearly, this is an ionic moiety where lithium is as positive, CH2, C triple bond N nitro. So this is an acetonitrile, which is the CH3, I guess. Okay, so this is having a negative charge. Now it will attack on a carbon which is having a hydrogen over here. So this is attacking on one position. Again, it has gone from eta 6 to eta 5, where the ONU are still intact because they are electron donating. So this position, and when we are using an RD, it will release this acidic proton. This is kind of very acidic proton, and it will be easily be taken up. And when this gets lost, it again forms from eta 5 to eta 6 moiety, and this becomes the desired product. And here the nucleophilic attack is occurring at the X orientation depending upon the steric hindrance of your metal carbonate. So this is the next example. The another example is of having a PFT. Arene metal carbonate complex is another example of its reactivity. Now we have to be very careful. Firstly, we need to see that this moiety is having a sigma donor pi acceptor capacity. So these form both kinds of interaction, sigma donor as well as pi acceptors. So this is a moiety, and when we have a very elevated temperatures, high temperatures are there. So these moieties which are having a sigma and pi both, they displace or they exchange with their arene moiety. They are not going to exchange with the carbonate. They will replace this particular arene moiety and gets attached in the, gets coordinated with the chromium, making a facial isomer. So to give you a brief introduction about okay, so if we have a metal and here are one ligand, this is one type of ligand, this is another type of ligand. You can either draw it in this fashion, which will make one triangle like this, other triangle like this, or you can make it like this way, L1, 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 L2, L2, L2. So this is one type of, and this is another type of. So these are facial isomers. When we have an octahedral. And another type is when we are having L1, L1, L2, L1, L2, and L2. So this is not making a proper, this has to go like this. So this kind of arrangement is called meridional isomer. So if you clearly see over here, firstly at elevated temperature, the take-home message is at the elevated temperature, the sigma donor or pi acceptor kind of ligands, they will replace your arene moiety, not the carbonyl. And they will prefer to form a facial isomer, which is having this kind of where PH3s are making one triangle and your carbonyls are making an inverted triangle. So this comes as this particular star triangle. So this was about the different reactivity of arene metal carbon complexes as we have seen. We'll just revise that we saw. Firstly, the preparation method was to use in presence of arene uh, metal carbonyl halide in presence of fused acid, which is AlCl3. That was the first preparation method. Second, what we saw was ligand exchange reaction. So here it changes it from neutral to a cationic species, maintaining that aryl valence cycle. It was from neutral to neutral, which we have seen. Then we saw different reactivity. What we saw that metal, arene metal, carbonyl complexes, they are more prone towards neutrophilic substitution reactions rather than electrophilic substitution reaction. So this concept is reversed for free arenes. So this is what we have seen, and we have seen some different examples. And also that arenes get exchanged with sigma donor or high ligands at high temperatures. So these are all the take-home messages from the lecture 26, where we saw the transition metal arene carbon complexes. The lecture 27 is also a further continuation of these particular complexes. Now we will see again we have an iodine, and this is an unusual. This is the reaction where we will see the unusual oxidation of the molecule. Here it is making 18 valence electron. It maintains its 18 valence electron, but here it is neutral. No charge on the molecule. Here it is cationic, and here it is an anion. So in presence of iodine, and if we take three molecules, it will form eta 6 arene, molybdenum CO whole 3. Since it is stable and neutral, Arene will come into picture with a positive charge, and the other it would form a dimer with NO2, NO molybdenum 2, I5, CO whole 6 minus. So this was established in 1986. This is some reaction where unusual oxidation state, oxidation of the molybdenum in the same reaction has been seen. Now, another kind of reactivity where we see a shift of eta 6 hapticity to eta 5. Then we have a metal CrO3, CO3 fragment over there. For example, if you closely look into this eta 6 this is a huge ring where eta 6 is found with the metal CO3. Now, in presence of this hydride, pH is a very strong base, you can say, or a reagent which can take up your proton release to release the hydrogen. And since we have already talked about the serine having any moiety, the protons become very acidic. So this H negative will take up your one H positive, leaving out one negative charge, and therefore H2 is being released. This happens at minus 30 degrees Celsius because we are dealing with strong bases or hydridonors. Now, earlier it was having only this one E over there and one H was 2H was there. Now, with the loss of one H positive, it is having a negative charge where the negative charge can move in between these three carbons. So, if negative is here, it can come in here and then this becomes a resonance. It is not clearly pictured over here. I can show you. So if we have benzene over here, earlier this was the case, and since it is going, we are giving H negative from KH, it is attacking on this H positive and giving over here, it will release H2. Now we have a benzene. This is having negative, one proton and big. So this is now in conjugation with it. It can come here and it can go here. So this is forming negative here and H over here. So therefore, the equivalent structure or the resonance structure that we can form is it is having. This shows that it is coordinating with A, B, and C. The negative charges delocalizing on A, B, and C carbon. So this is what is happening in this particular reaction. So now the negative has been formed. So at 30 degrees Celsius, now this having the negative charge, it can bind easily with the metal, making it negative. Now this becomes the CP ring, CrCO whole 3. Since now chromium is having negative charge, it can easily attack on any positive moiety. So therefore it attacks on the electrophilic alkyl moiety, and therefore R gets attached with the chromium. Now at high temperatures from 30 to 50 degrees, this again goes from this eta 5 to eta 6 transition, and R goes on that earlier position from where we have taken up the H positive because it was still coming as an electrophile only. So R it is coming at a H position. So this is a eta 6 to eta 5 transformation where one electrophile is getting exchanged with another electrophile, but having a transition from the eta 6 to eta 5 and coming back to eta 6. So here it is eta 5. A very interesting example. Now you need to be careful about the KH what you are using. Then also the H2 and how the carbons are coming into picture and where the moiety, the double bond is sitting into picture and how the chromium is getting negative charge, which is attacking on the R positive moiety. Now another example of eta 6 to eta 6 shift. Earlier what we saw was eta 6 to eta 5. Now we have an example of eta 6 to eta 6. That means from one arene, it is going to another arene. So to distinguish these two arenes, the one proton has been exchanged with the deuterium. This is nothing but your deuterium. And at higher temperatures, very high temperature, this is bound with this particular arene, which is eta 6, and now it is bound with this particular, which is devoid of any deuterium, and it is also eta 6. So it is eta 6 to eta 6 shift, which has been seen in 1988. Now, some examples of benzene cyclopentadienyl complexes. Earlier, we were looking around the metal with carbon and arene. Now, the question is of benzene cyclopentadienyl complexes. That means the complexes which are having both 5-membered and 6-membered rings. So, as you can see in the product. So, here we have to take a metal salt, general reaction, where it has been taken a manganese chloride in presence of any CP, which is a reducing agent also, where it's a source of C5H5 also. And this is a Grignard reagent, where it is important to have R is equals to C6H5 or any arene molecule, 6 number. In presence of solvent AHF and water, for the workup, we get an eta5 CP and eta6 arene with a 2% of it. The other side products would be, it could form a biphenyl, and manganese is coordinating with this, and this becomes, I guess, 15% or something. And another product that we have from here is biphenyl connecting with 2MH, and here CP and CP. This is 3%. So whatever the product that we are desiring, that we need to have on C5, eta5 and eta6, that means 5 and 6 number ring, that is forming in least amount, that is 2%, whereas the other products are having a bit more higher yield, where you can see that biphenyl manganese CP is the other product, which is 15%, and this is the another product with 3%. Other remains unreactive or something in that. So this was about lecture 27, where we can just have, where we have seen that we saw unusual oxidation state, oxidation of that molecular complex. Then we saw eta6 to eta5 transformation, shift of chromium CO whole 3 unit. Then in other step, we saw eta6 to eta6 shift. Then lastly, we have seen benzene metal cyclopentadienyl complex preparation, where the only disadvantages are desired product is in least yield. The product reviews very less. This is from the lecture 27, the paper messages. Now we are looking at another type of arene cyclopentadienyl complexes, because we have introduced it. Now, if you'll see the reactivity, how it is going to react with different nucleophiles or electrophiles. So our CHCl is nothing but an electrophile in presence of ileous acid. So here it is having a different kind of reactivity, where the mechanism is not known till now, but this titanic species come and attack on this particular 6-number ring, and therefore ring expansion happens. From 6 to 7-member ring. So here it is C6 and here it is C7. So which the C7 has come from this particular carbon, and this has been designed in 1966 by Fisher, maintaining the low temperatures in presence of pure acid. Now the ring exchange again, only we have 2 CP rings, but only one ring will be exchanged at one time. So we have a ring in presence of pure acid again and the metals. After workup, we will be ending up having a C6 moiety, replacing the C5, and the cyclopentadienyl ring will be out. So the take-home message is only one ring would be exchanged at this condition. Now, talking about in presence of sodium amalgam, as we know that it's a reducing agent, it will reduce the metal oxidation state. As you can see, it was an 18 valence electron complex, where one side it is CP. Other side, it is C6H or Ne6, where all the hydrogen have been substituted by methyl. So it is in +2 oxidation state. When we use the sodium amalgam over here, it goes to +1 oxidation states. That becomes a 19 valence electron radical complex. This is now a radical complex where the oxidation has been changed. But if we use a sodium borohydride, which is also a hydride agent, earlier it was sodium amalgam, which could only affect the oxidation state by giving the electron. But sodium borohydride, sorry, it will give an H negative, which can easily attack on one of the arene carbon where it has attached, and therefore it has gone from its eta 6 to eta 5 now, and one hydride has been attached on this particular ring. This also results in 19 valence electron radical bonds. So you need to be careful when you are treating with sodium amalgam. It will affect the oxidation state by giving the electrons. Sodium monohydride will also do the same thing, but it will also give that hydride H negative. Now, another reaction where you will see that if this complex is having C6H6 ruthenium moiety, how it transfers. So, for example, this is a dimer where we have C6H6. If I draw over here, one Cl, ruthenium, Cl. So this was a dimer, and here we are using titanium Cp, where it is positive, and this is the thallium Cp, I guess, positive and negative, a source of Cp. And in presence of ethanol, it is now getting reduced, and therefore, one of such complex it would be having a C5H5, and here it is C6H6. So how this particular moiety is being transferred to this particular thing where Cp gets attached over here, and since we are having a outside anion, P is 6 negative. So this is the reaction where we call it as a C6H6 ruthenium unit, which is transferred from one particular complex to the other. So going from dimer to monomer, having in the complex a C5H5 and C6H6. Another reaction where C5H5 ruthenium unit has been seen transferring. For example, if we have this particular, again starting earlier, what we saw was having this cationic complex where C5H5 and C6H6 together. Continuing with this particular reaction, how it is going to help in having the different quantities. In presence of solvent and photocatalytically, all the arenes will get exchanged by the solvent. And there are the solvents. For example, if you take CH3Cl or pyridine in that case, because it is happening photocatalytically or thermally also. And then when we have C6Me6, which is nothing but your substituted benzene ring, methyl substituted benzene ring. So it will replace and exchange your solvents with this C6Me6, maintaining this temperature. And then you again have this particular hexamethyl substituted benzene ring, which we were seeing over here. So this was the product that we found from the unit transferring reaction, and how this continues when we have a C5H5 ring. And it is now this particular unit, this whole unit, or we can call it as this whole unit, has been now transferred to this particular thing, and then we are having this complex where substituted arene is there. So this could also be a one reaction where not direct, it is happening. One arene is exchanging the other arene, but it is happening to other solvents and all other mechanisms. Then we have a cyclohexadiene complex to arene complex. How this goes to this particular moiety. So firstly, if you will see PH3C, this is a carbocation. Since it is having a positive charge, it is having the tendency to take up H negative very easily. So it takes up this, as we have already seen, this is an acidic proton. It will take up the H positive, therefore the negative will come into picture. And since that positive has come into picture, so it will take up the charge where oxidation would happen. And then since the negative would be inside this particular molecule, so it becomes an eta 4. This was earlier it was eta 4, then it becomes eta 5. Another moiety is there which will take up another proton, and therefore it will become an eta 6, which is a neutral thing. And as you can see, cobalt 1 to cobalt 3 has happened. So successive removals of two hydrogens happen if we are using 2 moles of PH3C, which is the calcium. Now in the lecture 29, we will be looking at some other examples of metal-ligand cyclodiene complex, and new ligand would be introduced, which is C7H7. So firstly, we will see that what was the first triple decker complex. Triple decker is nothing but when you have the sandwich complex, where not only one metal is there, two metals are there, which has been sandwiched between a particular CP or C6H6. As you can see over here, we have used C5H5, that is CP, and C3H5, which is 2 times, and in presence of the C6H8, which is going to replace the C3H5 at 100 degree, it is making a bond with CP, vanadium, C6H6, and again a CP, which is C5H5. It's a 26 valence electron species, where the parameters, this is with the bond distances of the CP with the vanadium is 192, and vanadium with the benzene is 170 picometer, making it clear that C6H6 is making a strong bond with the vanadium because of the less bond distance over here. Then triple decker, we have with only the arene ligands. There was a combination of CP and arene. Here it is only with the arene. So it is happening in gaseous state, where chromium in gaseous state and this C6H moiety in gaseous state, you can call it as ligand vapor co-condensation method. So this we have read in last lecture also, how in gaseous state the metal and the ligand stay condense together to form these kind of moieties. And here it is substituted removed, and this is a 13 valence electron complex, where the bond distance between upper and middle is chromium, it is 160, whereas the middle benzene, it is coordinating with both the metals, therefore the bond distance is small. Now, so up to this, we have talked about the C6H6, the arene kind of system, where it has coordinated with the metal having carbonyl moieties also. We have seen the reactivity. And we have also seen when C6H6 is there and other side it is having C5H5, which is CP. So how the reactivity changes and how it is reacting when you are having certain nucleophiles or electrophiles. So depending on the surrounding in the scaffolding of your metal, the reactivity of your arene will definitely be changing. Another and the last thing that we have read in the last two lectures of this particular week was about the C7H7, which is another. So earlier we have seen C5H5, C6H6. Now we are looking at C7H7. So this is another ligand, which is isopi-electronic with C5H5, because this is 6 electron, C6H6, which is equal to 6 electron, and C5H7, which is also 6 electron, maintaining the aromaticity. 4 n plus 2 5. So in eta 7E C7H7 complex, the troponium character may not be necessary. So not always it would be in this particular form. So also they can interconvert from C7H7 to C7H8 and vice versa. And normally early transition metals, for example, titanium, scandium, vanadium, chromium, they will tend to form metal complexes with these kind of moieties. So we will just look around what are the possible metal complexes are there with C7H7. So C7H7 and C5H5, these are a combination of both 7-membered and 5-membered ring, where these are the possible metals with which the complex has been seen. Then we have a cationic species, because we are using a vanadium chromium manganese, so it can also be existing cationic species. Then only particularly this could be a sandwich complex, where both the ligands, also others are also sandwich complex, but this is the homolytic, where both sides is a C7H7. Now here it's a combination of 7 and 6-membered rings. Also, this is a combination where we are having C7H7 metal carbonate. And different examples are there with rhenium and iodine and other. So these are the possible metals which have been seen to coordinate with C7H7. Mostly they are belonging to the early transition metals. And also their combinations are also occurring where we are having 7-membered rings with the 5-membered ring combination, 7-membered with the 6-membered ring combination, 6, or we are having a carbonyl species. So some of the examples of C7H8 where we have seen that either it could be possibly occurring as a small p. So 1, 2, 3. So this is C7H7. And if we have so here one extra electron is there. So this will bind C6. So this is C7H8. So these are also some examples where C7H8 is binding, where this is also complex where zirconium and molybdenum is meeting. Then a combination with the 5-member ring combination with carbonyl. And also in bridging mode, we have seen how it is combining with a metal carbonyl species. Now we will look at the preparation. Preparation is not very hard. We have to take a metal carbonyl. Here it is has taken the vanadium carbonyl complex, where it is in 0 state, and we are treating it with C7H8, which the structure I've already talked about. Since at higher degrees, it will release the carbonyl also because we have to exchange it, and also loss of H2 would happen, and therefore it will end up having the C7H7. So byproduct would be this also, where it is cationic angular and angle complex product would be having a cationic and second half is an angle over there. Another is, firstly, it's a simple reaction of metal carbon with that C7H8, or if we have a combination, we want to have a combination of two different rings, like C5H5 we want with a 5 and a 7 ring, right? So we take their cyclopentadienal metal transition metal carbonyl complex is there and treating it with C7H8. This is also occurring at high temperature. Where the similar process of release of carbon monoxide with hydrogen, it will give you a radical complex where both 5-member and 7-member rings are existing. Another most important kind of example you can see, again for synthesizing the C7H8, we have taken a metal carbonyl earlier what we were seeing, but with vanadium it was giving C7H7, making a radical. If we are taking a chromium or molybdenum, it will give you a C7H8, where it is binding with eta6 only. So this is possible for chromium, molybdenum, and tungsten. Now we already have seen if we have a carbocation, it will definitely take up that H from this particular moiety and releasing the positive bond of metals. So since this C positive, it will take up this particular hydrogen, and therefore totally it will be having a positive charge. And as we have seen, C7H7 positive, it becomes an aromatic species. Therefore, this resonance has come in picture. And when we are having a toluene, it will replace these P carbon monoxide because these 3 CO would be equal to 1 toluene molecule. It would be 6 electrons. This is nothing but an arene complex at a thermal condition. We are having a cationic complex. Now, if we start with this metal carbonyl and treating it with RCN. RCN is nothing but your acetonitrile. Arsine is nothing but your nitrile, and R could be anything, then methyl ethyl propyl group. And since arsine is also a 2-electron donor, so it will replace your 3 carbonyl, giving RCN thrice and CO thrice. When we are heating it with C7H8, so this is a solvent molecule, it can easily be replaced by C7H8, which is the arene. So these are kind of substitution reactions that we are talking about. This could be a simple route. This could be one route from where firstly we have a metal carbonyl treating it thermally, we are treating it with C7H8, making it a complex, and then treating with a carbocation to make it uh, a this particular species where we have a tiny species, and then we are treating with the toluene to have a toluene over here. Hello, can you hear me?
Okay, ma'am, can hear.
Okay. So, I guess you have joined very late. It's like 15 minutes left to end of this meeting. So, do you have
Sorry,
any?
ma'am, forgot that. Forgot
No, that is not an issue. You can just go back and see this video, which
that.
I'll be uploading today. But do you have any question regarding the week 6? Because even if I'll start explaining, I don't think that you will be able to grasp it because there are 10 questions and you have to go back to the lectures. Do you have any question regarding this or any earlier, whatever the doubt you were having?
No, ma'am. No, ma'am.
Okay. So I would suggest that once I'll end up this meeting, I will upload it and you can see all the videos. So the timing is from 6 to 8. So it is better if you can join early and you can be with me when I'm discussing all these questions. So there itself you can ask me the questions. Okay.
Okay, ma'am. Okay, ma'am.
So this week 6 was nothing more about, it was about this C7H7 kind of ligands and arene kind of complexes, their reactivity, their bonding properties has been explained. So I have taken up I will even share this presentation where I have explained each and everything. Even if you have not attended the lectures, you can just go through these things one more time and then you will be able to solve the questions very easily. They are very straightforward. So if once you understand the mechanism, that is straightforward to answer.
Okay, ma'am. Okay, ma'am.
So if you have any question, then I can wait. Otherwise, I can stop this meeting. I can end this meeting.
You can stop. We can ask. I will ask question next class.
Yeah,
There is
next
class
class
in next
Tuesday.
week.
Yeah, every Tuesday, 6 to 8. Rather than joining this late because now the session is about to end, it's better you can come at 6 or maybe at 6:30 or something that I can start. And there in the first half, I am explaining all the basic concepts which professor has told in more details. and then we are solving the question problems. If you are attending at the very start, then you will be in line with me. Okay, this is the problem that you are facing difficulty, and I can explain right away. But if at this particular moment when we are only having 10 minutes left, then it's very difficult to understand like what kind of questions you are having, and also you have not gone through the lecture. So it is better next week, Tuesday, 6 to 8 p.m. Okay, that would be helpful for you to attend the exam. Otherwise, if you are missing all these assignment questions, then it is better to address these things when you are watching YouTube. But when I'm having a live session, then you can directly ask me a question. I could better help you when you are asking me questions directly over here. Okay.
Yeah, I had class, so I get late.
It's okay. You can go back and see that. And I would like to have you in my next class from 6 to 8 so that we can have a better understanding in whatever the questions or queries that we are having. So it would help you in preparing for your examination. Okay.
Okay, thank you. Okay,
Yeah,
okay,
I
thank you,
will
ma'am.
end up this meeting. Hope to see you in the next week, and we will see the week 7. Even if you have any problem regarding the week 1 or week up to week 6, you can just ask me any question regarding that. That is also feasible for me to answer. And we will be taking a week 7 things. We will first discuss the basic concepts, and then we will go for the questions. But you can come up with any question that you are having. So this is not like
Okay, thank
mandatory
you,
that you
ma'am.
have to ask for the week 7 only. You can ask me any question. Okay.
Thank you, ma'am. Thank you.
Yeah. Okay,
Okay,
then I
ma'am.
will end up this meeting. So take care.
Okay,
Bye-bye.
ma'am. Bye.